We are now looking at the principal exercises. Number 4 says prove that the limit as x approaches infinity of f of x equals the limit as t approaches 0 from the right of f of 1 over t if these limits exist. So what we're going to do is we are going to start off by saying, suppose that the limit as x approaches infinity of f of x equals L. This is what's shown in this graph here on the right. Now we're going to say that then for every epsilon greater than 0, there is a corresponding positive number n such that f of x minus L, absolute value, is less than epsilon whenever x is greater than n. So all that means is, if we take an x greater than n, so let's first look at the graph and illustrate it there. So we take n, let's say we take n as this value here. So this is n. Then this will be f of n. So what we are saying is that if we take any x greater than n, so if we take any x to the right of n, then the distance between f at that x value and L will be less than epsilon. Epsilon is this distance. So epsilon is the distance between L and f of n. So if we choose an x greater than n, so if we choose an x to the side of n, then the distance between f of that x, so let's say we take that x, this is going to be f of that x. The distance between L and f of x, this little part here, is less than epsilon. Right, so that's what we've said so far. Now, if we let t be equal to 1 over x, so if t is 1 over x, then x is greater than n. This is if and only if 1 over x is less than 1 over n, and we also know that 1 over x has to be greater than 0, since we said that n is a positive number and x is greater than n, so x has to be a positive number, so x has to be greater than 0. And this is if and only if t is between 0 and 1 over n. What this means is, thus, for every epsilon greater than 0, there is a corresponding delta, which is greater than 0, and delta is simply 1 over n. such that the absolute value of f of 1 over t minus L is less than epsilon whenever t is between 0 and 1 over n. Or, instead of 1 over n, we just write delta. So, this proves that the limit as t approaches 0 from the right, which is what happens when n approaches infinity, then this approaches 0 from the right, the entire thing, of f of 1 over t has to be equal to L, which is equal to the limit as t approaches infinity of f of x. And that's the end. Number 5. Let P and Q be polynomials. Find the limit as x approaches infinity of P of x over Q of x if the degree of P is less than the degree of Q. Right? So the degree of P is less than the degree of Q. Now, what we're going to do is we are going to divide the numerator and denominator by the highest power of x in Q of x, which is our denominator. What's going to happen then, since the degree of the numerator is less than the degree of the denominator, and we've divided by the highest power of x in the denominator, our numerator is going to approach 0, but not our denominator. So what does that mean? If the denominator approaches 0 but the numerator doesn't, it means that the limit as x approaches infinity of P of x over Q of x is going to be 0. Number 6. Find a formula for a function that has vertical asymptotes x equals 1 and x equals 3 and a horizontal asymptote y equals 1. Well, the first thing we can do is if we look at our vertical asymptotes, it means that the denominator of the function that we're looking for, the rational function, has to have the factors x minus 1 and x minus 3. So they have to be factors of the denominator of the rational function that we are looking for. Right. The next piece of information is that our horizontal asymptote is at y equals 1. So we know that the limit of the function that we're looking for as x approaches plus or minus infinity has to be 1. We have some more information about that function by now. We know that the function has the factors x minus 1 and x minus 3 in it. So let's just call our numerator some polynomial p of x. If we multiply our denominator out, then we get the limit as x approaches plus or minus infinity. So we have x squared plus 2x minus 3. And now I'm going to divide my numerator and my denominator by the highest power in my denominator. So I get p of x over x squared over 1 plus 2 over x minus 3 over x squared. So what is going to happen to these two terms if x approaches infinity? Well, they will both approach 0. So this one will approach 0 and this one will approach 0. So what this means is that the limit as x approaches plus or minus infinity of p of x over x squared, sorry, that's a mistake, it's supposed to be a 1, has to be 1. And that means that we can set p of x equal to x squared, because then we have the limit as x approaches plus or minus infinity of x squared over x squared, which is just 1, which is equal to 1. So a possible function such that we have vertical asymptotes at x equals 1 and x equals 3 and a horizontal asymptote at y equals 1 will be the function f of x, which is x squared over x minus 1 multiplied by x minus 3. So this is one possible function. Lastly, we're looking at number 7, which says find the limit as x approaches infinity of f of x if we have f of x between 4x minus 1 over x and 4x squared plus 3x over x squared for all x greater than 5. So we don't really have to worry about the x greater than 5 because in the limit that we're looking at, x is approaching infinity anyways. So what we're going to do is we're going to look at the limit of 4x minus 1 over x as x approaches infinity, so the left-hand side. This is going to be the limit as x approaches infinity of 4 minus 1 over x, and that is simply 4. Now we look at the right-hand side, so the limit as x approaches infinity of 4x squared plus 3x over x squared is going to be the limit as x approaches infinity of 4 plus 3 over x. And what is that? Once again, that's 4. So we can say by the squeeze theorem, the limit of f of x also has to be 4. So therefore, by the squeeze theorem, the limit as x approaches infinity of f of x is 4. This is the end of this week's video.